Yeah, good day once again. It's been a while since we met. For the sake of the incoming exams, I would like you to spare some time and we go through these few tutorial questions and see how best we understood the fluid statics. I'll try and see whether we can get something on the fluid dynamics part, okay? So that everything will work out accordingly. But you guys shouldn't be panicked. Don't get panicked because it's just a normal distance. Someone will say, it's hard in area. All right. So I have 10 questions here, all on fluid statics, okay? The first one, some of them, I think we've gone through a majority of them, just a few that we haven't, and we'll see how to solve them and then proceed with how to execute the exams, okay? All right. So first of all, as an objective, we are, like I said, we are going to solve problems using concepts learned in what? Fluid statics, okay? And the first question, we saw this earlier, the hydraulic jack, which has the dimensions as shown, okay? Now realize that if one exerts a force of F, of value 100 newtons on the handle of the jack, they're asking us to find the load, right? The load that it can support the jack. So this time around, we are neglecting what? The lifter. This is this. So we are going to use the Pascal's principle. As we can see that loop here. Okay. All right. So first of all, this is the lever. If we take BC and that stretch where we have the force F of magnitude 100 newtons, okay, applied here. And the other dimensions we can see, we have 3 centimeters here, 30 centimeters, and then the diameter 1.5, which we can use to estimate the area of that section, A1. And then the diameter here is 5 centimeters. We can use that to estimate the area A2, okay? And with that, we can play along to obtain the load that the jack can support. All right. So the free body diagram, if we take the lever, okay, now the lever, we have these dimensions there. First of all, the force 100 newtons is here. Remember where the B is, right? And then the C. Over there in the diagram, B is over there and C. So we've just taken that stretch here as the free body diagram, the first free body diagram, okay? Now, the dimensions are as follows: 30 centimeters, which is 0.3 meters, and then 5 centimeters, 0.505 meters, okay? Now, notice something here. We detach this lever from one part of what? The Pascal joint, that's the loop, okay? So as it stands now, we don't know the direction of the force. We actually know, but let's see how physics can help us to get that, okay? That's using Newton's laws of motion. All right. So we call this the free body diagram 1. Now, considering the free body diagram 2, where we have the static fluid in that enclosed section. Okay. Over here, we are looking at the forces. Remember, the forces are going to be compressive, acting on the surface of the fluid. Now we have F1 and F2. Now, if they are acting this way, downwards, that means the other force that will act on the B will be what? Yeah, I know what you just thought of. It's upward. Yeah, that's good. Good. So we have it this way. So basically, this is the complete free body diagram. But to make things more clearly, let's see here. Over here, we need to obtain the area for the smaller section. Okay, which is A1, and we know the diameter to be 1.5 centimeters. So if we convert everything to meters, we have 0.015 meters, and knowing A1 is a cylindrical slot, so it's going to be pi d squared on 4. So if we put in the values, we end up having 0.000177 meters squared. Okay, all right. Now we do same for the other section and obtain the A2 to be 0.001963. Okay, Notice the decimal places. We are using what? 6 decimal places here, okay? Good. Now, with reference to the complete what problem, the diagram for the problem, we can see clearly that everything has been what? Accounted for. Okay, F2 is acting here, but remember we are taking what? We are neglecting the weight of the lifter. So the only force acting on this surface is just F2. If we were to consider the weight of the lifter, this time around we would have added that weight, okay, to the F2 to be the combined force acting on the area too, okay? All right. So basically we have 3 diagrams here. We have 1, 2, and 3, okay? Good. So now let's see the analysis. We have the lever here. So first of all, we know we need to estimate what? F1, and we've done this already. It's just a reminder, or let's say, someone will say a recap class, okay? All right. First of all, if you can recall, we said to be able to estimate F1 or determine the value of F1, we need to what? Do some moment calculations, right? We have to take moment. And here we are taking moment about what? Point C, right? You are confused. No. Let's see. Now, if we take moment at point C, what does that mean? It's like we are holding point C as a hinge, right? And then we consider the forces individually. Now, and see the sense that the force will have on the body. Now, if we hold C as a hinge or we nail it, now we exert only F. Where will it go? This way, right? That's what? Anti-clockwise. And then F1 about this point, if we hold this and we exert F1 on the lever, it will turn the lever clockwise, okay? Clockwise. So by doing that, we now know that we have anti-clockwise and clockwise. But we can also use the assumption that summation of forces about point C such that clockwise moment positive, right? They are positive. And we equate that one to 0. So when we do that, we realize that since F is anti-clockwise, it will give us what? Minus F times the moment arm. And the moment arm is what? That perpendicular distance measured from what? The line of action of the force to the moment what? Center or the pivot, okay? All right, so if we sum this and that, we are going to have what? We are going to have, let me see. Oh, sorry, hold on 1 second, okay? 1 second. Yeah, sorry about earlier. When I was writing the value for the moment arm, that's the distance, let's say the distance between points B and C. Earlier, I made it 5 centimeters, but from the problem, it's actually what? 3 centimeters, meaning 0.03, not 0.05, okay? All right, so with that, this part, we've already estimated it. Okay, now here, this is where I got to realize it, okay? So it's actually, over here between point B and C is actually 3 centimeters, not 5 centimeters. So we go with what? The 3 centimeters, okay? So 0.03 meters. Now, if we use this, okay, for the analysis, from there, if we take moment about point C, such that clockwise moment is positive and then anti-clockwise negative, we sum them. Already we said F will give us what? Anti-clockwise moment about point C. So that one, the force itself multiplied by the moment arm, which is what? A measure from here to C is what? 0.3 plus what? 0.03 meters, which is actually 0.33 meters times the force. That's why we have what? F times what? 0.33 all into bracket negative, right? Negative value. And then plus F1 is going to give us clockwise. It's turning about the clockwise direction, okay? This way. Okay. So that will be F1 times 0.03. And when we sum that, we are saying we equate to what? 0. Okay, that is why, or that is what this statement, let me circle that for you to see. This statement means, that's what it means. Okay, and we actually did that by equating it here. Okay, all right, so let's see. Now, having said that, we can now make F1 the subject from here by taking this to the right hand side of the equal sign. Okay, and then we divide through by 0.03, and we have what? F1 to be equal to blah blah blah. We know F to be what? 100. So all this, we have what? 1100. That's, sorry, 1100. Okay, newtons. Okay, that one gives us the value of what? F. But remember, that's not the value we are looking for. We are actually looking for what? The load that the jack can support, which is actually F2. So now, having obtained that, we can use that to obtain what? The F2. Now let's consider the free diagram 2, free body diagram 2. Now, if we consider that we know F1 is now here, okay? Remember, F1 has the same value on the surface. So if we consider the fact that Pascal is saying that the pressure remains constant, right, throughout the system when there's a disturbance, so, all right, meaning that P1 at this surface is the same thing as what P2 at this surface. So if we use that assumption, okay, in that case, we know pressure to be equal to what? Force, okay, per unit area, yes. You thought. So let's see. So we have what? For P1 is going to be what? F1 on A1. And we are saying that one is equal to what? P2, which is F2 on what? A2. Now I can obtain F2 by making that one the subject. So if I do that, I have A2 on A1 times what? F1. And remember, we calculated the value for what? A2 and A1 over here. Look at them. A1 is here. And then A2 is here. So if I use that, I'll end up having 12,199.14 newtons, okay, to be F2. Okay, that's in estimation, or let's say approximation, we have what? F2 to be approximately 12.20 kilonewtons, okay? So that brings us to the first problem, and we are done with that, okay? All your questions should be addressed to me via Telegram or WhatsApp, or you can call me, okay? And then we'll go through slide by slide and we'll see how best we can solve that, or use the time or the minute associated with it, okay? All right. So we'll move on to problem 2. Good. Now, problem 2, we tackle this. Here we are saying that water occupies the bottom 1.0 meter of what? A cylindrical tank, on top of which, that's on top of the water, is what? A 0.5 meter of what? Kerosene. That's a stretch, which is open to atmosphere. So that should tell you something. It's open to atmosphere. There's a hint there. Now, yeah, we'll get to that hint, don't worry. If the temperature is 20 degrees Celsius, what is the gauge pressure at the bottom of the tank? You see, it's interesting. I don't know what you are thinking now, but we'll see how best we can do that. So to solve this, we have the problem, but diagram, if we are using diagrams to show this or represent this, let's see how it will look like. This is the diagram. We are saying that water, this is not Y, please, it's gamma, okay? Gamma W, that's for water, okay, at 20 degrees Celsius, and then gamma kerosene at 20 degrees Celsius. So meaning the temperature here is the same. We getting it? All right. Now we are saying the water occupies what? 1.0 meters. This is what it means. So this is the height of the water. Okay. And on top of that, we have 0.5. So on top of that, 0.5 kerosene, right? Okay. Okay. We have the kerosene. Now, the asking is, what is the gauge pressure at the bottom? Where is the bottom? This place. Okay. This place. So they want the pressure here. So one way to do this is to look at it from this angle. We look at the pressure here, plus the pressure here, the pressure here, plus the pressure due to this level, plus the pressure due to this level will be equal to the pressure at the bottom. No, so if you can recall. All right. So let's see how we solve this problem. Now, let's see what we've been given. We've been given some data. What is it? Over here, if you use the textbook I gave you and you refer to table A9 and A10, okay? Gamma, okay, that's a specific weight of kerosene at 20 degrees Celsius. It's actually what? 8,010, okay, Newton per what? Cubic meters, okay? And for water at that same value, that same temperature is for 9790 Newton per cubic watt meters. Okay, all right. So let's see. I actually came up with two ways to solve this problem. I named one direct and the other one, well, we'll get to that part. So here the direct one is just to look at what? The pressure at the bottom, which is this, okay? Pressure at the bottom. We are saying that this is actually equal to what? What I didn't bring is actually what? The pressure on top here, okay? Because it's open to atmosphere, I assume that part to be zero. So I didn't actually consider it at all. So I focused on what? The pressure due to what? The height of the kerosene here, okay? But if this place was to be sealed, we would have considered the pressure at that point and added to the pressure due to that. And then add that one to the pressure due to this, okay? And put it there. So here, because it's open to atmosphere, that pressure to the surface here is what? Zero. So I didn't talk about it, but we'll look at it in a different angle, okay? All right, so here I'm saying that gamma K at 20 degrees times what? This. Remember, pressure is actually what? Rho GH, right? And rho G is actually the gamma. So H is the 0.5 here. So let me see whether I can write something here for you to recall them, okay? I'm saying that, remember, gamma is actually equal to what? Rho G, okay? And we know pressure, rho G H, okay? The hydrostatic pressure, okay? Good. So now that's the same idea. So we only focus on the one due to this height, okay? Now, plus gamma of what? Water 20 times 1. So likewise, we are talking about this height, okay? That is it. So now we just do substitution. Gamma and that, we know the value to be 18, whatever, times that plus this. So at the end of the day, we have P at the bottom to be what? 13,795, the unit Newton per what? Cubic watt. Sorry, square meters. And the same thing as what? 13.80 kilonewtons per watt meter square. That's actually what? Pascal, kilopascal, okay? All right. So let's see here. In other words, this is what it means. So please be conversant with the unit. You don't know when and how you are going to be asked to show the right unit, okay? Please, this is very, very important. As student or as engineering student, you should be very conversant with your SI unit or any unit that you'll be dealing with, okay? Good. Now, let's look at the second alternative, okay? Alternative 2. Now, here we apply what? The hydrostatic equation in the kerosene. Remember, with the hydrostatic equation, we can consider 2 points. For instance, with the kerosene, we are looking at what? 2 points within the kerosene, but it's always better to look at the boundaries. That's the top surface of what? The kerosene, and then the bottom surface of the kerosene. Yeah, I know what you are thinking. Yeah, the bottom surface is also the top surface of the water. Yeah, we will get to that, okay? So we look at the top surface of the kerosene and then the bottom surface of the kerosene. So if we call this part 1 and we call this part 2, we are going to apply the hydrostatic what? Equation. That's the pressure equation. And remember, we have the piezometric. I'm talking about the piezometric here. We'll get there, okay? All right. So if we consider that part as 1, okay, then we are saying that over here, okay, over here, I don't know whether you remember the hydrostatic pressure equation. Let's see here. The hydrostatic pressure equation. That's what I mean. Remember, we have P plus gamma H is equal to C, right? It's constant. This is what we are using now. This assumption here is telling us that no matter the location, if we are in the same fluid, that's the same gamma, once gamma is constant, okay? If we sum P and then gamma H, it should be the same, it's constant throughout the same fluid. So if I consider point 1 here and point 2 down here, okay, whatever sum, if I say P1 gamma H1 plus gamma H1, it should be the same thing as P2 plus gamma H2. That is constant. That's what we mean, okay? So basically, this is actually saying that P1, if we have 2 point plus gamma H1, remember, if you go through your notes, you know we've talked about this, is equal to P2 plus gamma H2, okay? All right, so that's what we are dealing with now. So if we apply at this point, I'm now going to have what? P1, here we are here, okay? P1 plus gamma, what gamma we're talking about? The gamma of the kerosene, right? Times Z1, okay? Z1 is actually like the Z. Remember, it's just a piezometer, it's just the H here, okay? All right. So this, we are saying that that is the sum of the pressure at point 1. Now let's go to the bottom. The bottom 2, we are saying that this is equal to what? P2 plus gamma K 20 degrees Celsius times what? Z2, okay? Now, remember, we need to set our reference, okay? We need to set our reference in order to estimate the value of what? Z1 and Z2. All right, so if we use the bottom as the bottom of the tank, that's P as the reference point, okay? We use that. What do you think will be the value of Z1? To get to Z1, we'll measure from here all the way up. That Z1 will be what? 1.5 meters. Yes, some of this to that. And Z2 will be what? From here to here. And Z3, if we take the bottom to be Z3 will be 0. Okay? So take note of that. Now, if we do that, that is what we are going to have. Now, meaning we've been able to estimate Z1 and Z2. And also take note that at the surface here, P1 is exposed or open to atmosphere. So P1 is 0. The gauge value is 0. So this implies that we only have this term here and that term. And remember, we are looking for what? P3. So if I'm able to estimate P2 here, I can use that to estimate P3. All right. So this implies that P1, here we are taking the one after the other, plus gamma this times 1.5, okay? And this is equal to a P2 that. And remember, we've estimated these values too already, the gamma K and that. All right, so this implies that my P2 is basically what? This, if I make P2 the subject here. So upon substitution, we end up having P2 to be equal to what? Remember, it's minus because we are taking this value across. And if we do that, we have P2 to be this value. Okay? All right, 4,005 Pascal. So now at the kerosene water interface, if we consider the bottom part of the kerosene, which is now the top surface of the water, P2 kerosene is equal to a P2 water. So I can still use the pressure there. Remember, the pressure there is just like the weight on that surface, okay? All right, so if we use that, now we are going to consider, remember, the interface I'm talking about is this part, okay? Let me show you here. This is the part, okay? That's where the arrow is indicating, okay? All right. Sorry. So now if we apply the hydrostatic equation in the water, we have this. Remember, we are now looking at point 2 and then the bottom surface of what? The water, okay? The bottom part of the water. So at point 2 is P2. This time I remember it's gamma W, not gamma K, kerosene. We are assuming that gamma is now uniform because we are assuming the fluid to be water now. All right, so times that. And this is equal to what? The third point here, that's the bottom. So P3 plus what? Gamma and C3, right? Good. So you don't worry. If you're not getting it now, replay it. You get it, okay? And if you still don't get it, just let me know. I'm there for you, okay? All right. So now from here, my P3 can easily be computed, just making it a subject here. And from here, we just substitute, right? And we end up having 13 what? 1,795, which is the same thing as what this, right? Yeah, I know it's long. Yeah. You are saying that. Don't worry. I can specify the type of method to use. I'll ask you to use the hydrostatic equation approach or the direct method. But if it's objective, of course, you go with the shorter technique, okay? All right. But if it's theory, then you get to do with the one I asked you to, okay? Don't worry. So here, if we simplify, we end up having what? 13.80 like we did here, kilopascal, okay? So that's it for question 2 or problem 2. Good? All right. That is super. All right. So now let's move on to problem number 3. Problem 3 is just like the first one, okay? I'm going to use one method and then try using the other method, okay? Which one do you think I'm going to use? The easier one or, no, sorry, the shorter one or the longer one? I don't know. Let's go on to the next one. All right. So let's see. This is the diagram we are dealing with. We have oil. This time the oil is what? 0.90 meters. And then the water is what? 2.10. Now, the temperature for the water or in the kerosene is actually what? 10 degrees Celsius, okay? We have 0.1, 0.2, 0.3. And this is the surface of the fluid. That's the oil, which is exposed to the atmosphere. So with the data given, we can say that we are fortunate because they've given us what? That for the water. Remember, the specific gravity of 0.8 form, that's the oil. It's having a specific gravity of 0.8. And remember, this is different from the specific weight, okay? Yeah, look through the definitions, the terminology, so you get to know that one. Now, and then it has a layer of what? 0.9, as you can see here, and then it's open. That is otherwise, sorry, let me read it directly from the listing. Oil with a specific gravity of 0.8 forms a layer 0.9 meters deep in an open tank that is otherwise filled with what? Water 10 degrees Celsius. Now the total depth of what? Kerosene or the water and then the oil is 3 meters. What is the gauge pressure at the bottom? That's section 3 of the tank. Take water to be this. Okay, now if we are using gamma of water to be this, we should be able to estimate gamma of oil. Okay, because we know that specific what? Gravity, let's say SG is basically equal to what? Hey, let's say, okay, it's just if we are using the specific weight, okay, it's actually Specific weight of what? Whatever fluid that we are talking about, okay? All over what? The specific weight of what? Water. Okay? So we'll see, we use that one here. All right. Now, if we look at this, the data given, since the specific weight of what? Water has been given as what? This. Okay? Now, I can use that one to estimate what? That. Because I know, like I said on the previous slide, SG, we can obtain that by saying SG, specific gravity of the fluid here is what? Oil. Okay? All over specific gravity of what? Sorry, specific weight of what? Water. So meaning the specific weight of oil, okay, is actually equal to what? Cross multiply. We multiply of water times what? Times SG, right? SG. So that is what they did here. So oil is what? 0.8 times that. And then we end up having what? 7848 Newton per cubic watt meters, okay? So this is what we are dealing with here. Please. Yeah, just be jotting your questions down, okay? Be jotting your questions down. Once you don't get it, you prompt me and then we'll see, okay? All right. So now let's move on to the continuation. Let's continue with it. Now, I'm using a direct approach. Don't worry. So we are talking about the pressure at the bottom, which is actually what the P3. So P at the bottom is equal to what the P3. And we are saying that, sorry, we are saying that P3 is simply what? The pressure due to what? The oil height. That's gamma of oil times what? The H, which is actually what? What is given here? Plus gamma of water plus times what? The height of the water. That's 2.1. So if we use this, at the end of the day, we end up having what? This, okay? Just upon substitution, which will finally give us what? And this, and upon simplification, we have what? 27.66 kilowatt Pascal. That's a gauge value, okay? So as your assignment, not necessarily an assignment for you to submit, just try this, pause the video, okay? And then try using the alternative 2 approach, and let's see how best that's using the hydrostatic equation within the fluid, okay? Let's use that one to see how best we can do that. So I'm pausing for like a minute. All right. Let's see. What do you have now? What do you have? Yeah, I can see you had it. But if you didn't get it, just visit the example 2 and then see how you can do that, okay? All right. So here, like I said, try using alternative 2 and compare results, okay? All right. Now we are going on, or we are moving on to an interesting what problem? That's problem 4. Let's look at what is here. This is interesting, right? It's been a long time you heard me. Don't worry. I'm here. And I know you are looking good. You are seated. Some of you are eating. Some of you don't know what to do in the exam. But don't worry. We won't go. You'll be fine. Everything will be fine for you. All right. So problem 4, we are saying that, yeah, the diagram looks funny, right? We have to look at how the dimensions are given. See, from this line to the more or less like the midsection, okay? From the top to this, from that to that. Yeah, it's interesting. We'll see. We'll see. All right. So for the closed tank, here it's not an open tank, meaning there will be pressure indicated by this gauge, which is PA 50 kilopascal, right? 58.53 kilopascal. And then PC, we don't know yet. So let's see. So for the closed tank with what? The boarding what? And tube gauges tapped into it. What is A, the specific specific gravity of the oil and the pressure reading on gauge C? It is interesting, right? Very interesting. So think about it. Yeah, so what do you think now? All right. So to find the specific what gravity of the oil, let's see what we do. Yeah, I'm just bringing the question here just to help us refer, okay, for reference. Now, the data given from the problem, we can see the major ones are these. We have PA to be that's 50,000 Pascal, PB to be that, but PC we don't know, okay? We don't know the oil and we don't know PC. That's what we are going to find, okay? They are the things that we are going to deal with. Now, for the analysis, this is what we go about it. We are saying that we need to find what the specific gravity of oil. So to do that, we need to first find what? The specific weight, right, of oil by applying what? The hydrostatic equation between the oil surface and elevation B. Look at something here. The oil surface is here. That's below the air. Because here, if we use the hydrostatic equation, meaning that within the same fluid, gamma is constant. That's the specific what? Weight of what? The oil will be constant there. So we can estimate that. We can estimate that. And once we estimate that, we will solve that problem, the first part of what? The problem, by obtaining what? The specific gravity of the oil. Okay? Good. Good. So remember, here, this is how we go about it. So that's, if we apply that, we are going to have oil surface. Let's say the oil surface, let's call the surface A, okay? The surface here. Not this part, the surface here, let's call it A. So if we call it A, remember the pressure on this surface is the same thing as what? It's air. It's uniform, it's distributed equally on the walls and then that. So the pressure here is what is actually acting on that surface. So it's actually PA. Now, so if we take the level here as A, so we have level A and then let's say level B, okay? So PA, the sum of the pressure here and then the gamma times the H. So we have PA plus what? Gamma of oil times ZA is what? The hydrostatic what? Pressure, that's the piezometric pressure at point A. Okay? So let me write this thing here for easy reference, okay? Okay. So let's call this part as A. Okay. And this part here, remember, is the B. Okay? All right. So at A here, at A, this point, this line here, this is what we are looking for. And remember, we said it's P plus gamma Z. Okay, let's use the Z instead of the H, equals C is constant. What that is telling us is that we have, if we have at point 1, P plus gamma Z, let's say this is at point 1, that's P1, Z1, is the same thing as what? P plus gamma Z at point 2. Okay, so that's what we are dealing with. So the point 2 here will be B and point A is point 1 is the A. Okay, all right, so that is what we are dealing with. So this should be equal to what? PB, okay, PB plus gamma of what, because it's the same fluid. That's gamma, okay, times ZB. So here we still don't know how to estimate that, okay? Now, it is up to us to use whichever elevation, or we need to set our reference point or the datum line. Now, if we use elevation B, that's this part here as a reference, this B, okay? Sorry, this part. Yeah, I think you can see it. This part here as our reference, meaning from here to this surface here, we should be able to estimate that as the ZA, and then the ZB is actually the same level, right? Sorry. The ZA will be this level, and then the ZB is just here. So meaning ZB is what? 0, and then ZA is from here up, which is what? 1 meter, okay? So if we do that, we put in the values. PA we already know, oil we don't know, the gamma of oil we don't know. So we can use that to estimate what? Gamma of oil. So this part will be 0, and then we just move this thing across. So we end up having what? Gamma of oil to be this, okay? 8,530 newtons per what? Cubic meters. This part here, if it's objective that I'm giving you, I'll give this value. So you might rush to pick this value. But remember, this is not what we are looking for. We are looking for what? The specific gravity, SG, okay? Yes, I wrote this one here just to serve as what? A reminder, because we need to look for this, because here I said finding the specific gravity, SG, okay? All right. So, but SG of oil is actually what? Gamma of oil over what? Gamma of water. So I need to just put in this value divided by what? The gamma of water, and this is what? 0.87. Now we have what? The value of the SG. So we need to find PC, okay? So finding PC, we are saying that here we simply apply the hydrostatic equation in water. So in water, we just consider what? This part here, okay? We need to first of all know the pressure here, and then that. But let's see, okay? Okay, all right. So if we are applying the hydrostatic pressure in water, we need to first of all know the pressure acting on the top surface of the water here, which is actually like the bottom of what? The kerosene. Sorry, not kerosene, the oil, okay? The oil. If we now know the pressure acting at the bottom of the oil, then we can say that that pressure is the same thing as what? The one acting on top of the water. So we now apply between this point, okay? Okay? And then this part, elevation C. Okay, and then we can get that done. Are we there? All right, let's see. So here we have P. So on top of the water, we have what? P oil, that's P of what? The pressure at what? The oil bottom. So the pressure of oil bottom. So the pressure at what? The oil bottom here. Not at BO, at this point here. Sorry. Let me use a laser. At this point here. Please, not here. So we are looking at what? The pressure at what? The oil bottom here. Plus gamma of water, okay, times Z of oil bottom. So, all right, the Z here. Remember this equation? And remember here? So we are looking at this surface here. So P at what? The bottom of what? The oil plus what? Gamma times what? The Z of what? The oil at the oil bottom. Okay. Now, this must be equal to what? The PC. PC is here, right? At this elevation. Let me draw that line too. PC. Okay, let me change the color to this. So we are looking at this PC here. And then we looked at here. That's the bottom of the oil. Okay. All right, so let's say we call this oil bot. That's the bottom, okay? Oil bottom. All right. So if we do that, now we are saying that's equal to what? PC here plus gamma of what? Water times ZC. So what is left now is to find what? The P bottom, right? So if we make PC the subject from this equation, we are actually taking this one across. So we already have P oil bottom here plus blah, 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 Z oil bottom minus gamma water times C, ZC, okay? All right. So now if we use elevation C as what a reference, that means Z of what? Oil bottom is simply from where? Here to here, which is what? 1. And then ZC is what? 0. So that one is established. So we know our ZC and then Z of what? Oil bottom. Please, it's as simple as that. Okay? Good. All right. So having established that, it means that since ZC is 0, this part is off. Okay, so our main focus is to follow what? P oil bottom plus gamma water times what? Z bottom. So if I use this, okay, I'm basically having what? The equation for what? Finding PC. So, but P bottom, oil bottom can be obtained by applying the hydrostatic equation in oil. Because if I now know that in the oil, I can establish this one quickly, right? All right, so remember, P oil bottom here, okay, is simply what? PB, okay, that's the pressure read by what? The gauge at B plus what? The oil, the specific gravity, sorry, weight of oil times what? That elevation, okay? Let me erase these things so that you can get to see this thing, okay? Okay. All right. So here we are saying the P oil bottom, right? At the bottom of the oil can be what? Obtained by applying the hydrostatic equation in the oil. Now, remember that these pressure gauges, okay, they take into account the pressure on top there and the pressure due to the oil, okay? Sorry, I'm using this thing. They take into account the pressure as a result of the air and then that of the oil here. So that one will give us this, okay? But to be able to establish this one here, we would have to use what? The elevation here, okay? So that is why we don't say the pressure of the air plus the pressure of the oil, blah, 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 that, okay? But we are looking at what? P of what? The PB, this one here, plus the pressure due to what? That here. And that will give us the total pressure at the oil of the, what? The oil bottom, okay? All right. So by doing that, we are saying P at the oil bottom is actually equal to what? The PB, this one here, okay? The pressure at this elevation plus the pressure due to what? This height, okay? That's 0.5 meters. So that will be that. And then from there, it implies that PB we know to be 58.53, which has been converted to what? Direct Pascal, 58,530 plus that. So gamma of oil, we know that too already. We've established that, where is it? 8,530 here. So we use that to obtain the pressure at what? The bottom of the oil, right? Now, upon substitution, we can estimate what or determine the value of what? PC. So upon substitution, PC is now P at the bottom of the oil plus what? Gamma water times that. And remember, when we do this, we can have what? The pressure at PC to be that, okay? That is very, very simple, okay? Now, let's take the last example and then the last problem, and then we'll end this, and then I'll record part 2 for the remaining 5 questions, okay? All right. So now let's move on to any question. Please jot them down and you get it. Okay, answer. So the last question here for this part of the tutorials on statics, fluid statics, is this one too, on the manometer. Okay, the YouTube manometer. So here they are asking us, what is the pressure of the air in the tank if L1, we know L1 is this small part here. Okay, sorry, is equal to 40 centimeters, L2 100 centimeters, and L3 80 centimeters. Take gamma of oil and gamma of mercury as was 7,850 Newton per cubic meters and 133,000 Newton per cubic meters, respectively. We are to neglect pressure changes in the air column. Here we are now moving, okay? All right, so here, let's see the next part. To solve this, let's consider the diagram again. Now, with consideration to the diagram, we are saying that if we use, remember, here we use the walking through method where we dive through what? The manometer. And as we go through, we take into effect whether going down is positive or going down is negative, whatever option you choose. Remember the general formula. If we move from, let's say, point 1 to point 2, remember we have what? The pressure of interest will be the one we'll be looking for here, which is P2, is actually equal to what? The P1, which is the free end of the tube, plus the summation of what? The pressure measurement due to downward movement minus the pressure measurement due to what? Upward movement. You can take it the other way around too, and you get it done, okay? So in application for this particular problem, let's see what we do. First of all, remember we have similar problems. Since we are moving down, if we move down to this point and we'll move down here, remember this height is the same thing as what? This height here, right? Because I'm saying that if we go down, it's positive. So if we come up, it's negative. So this and that will cancel. That's why I've ruled that line here to take care of what? The downward and then the upward reaction, okay? So that we don't consider them, okay, in our analysis. The next part to rule out, so meaning this part here is 0, the sum. The next part to rule out is this part here. When we get to this part, we will go up. It's the same fluid, air. And then we'll come down the same fluid. So this part 2, upward, minus, right? Downward, positive. So they will also cancel out and give us 0. So remember, we are only focusing on from here to here, from here to here, and then here to, let's see. Remember, the size doesn't matter, okay? So when we get down, when we get to this part, we can break here too, because we'll move down to this point, okay, and still move up to this point, because we are looking for the pressure here in the tank P2. So we'll move here up and then we'll go up. So moving down here too is positive and moving up is negative. So here too, it will cancel out, okay? So by default, we are actually looking for what? This height, this height, this height, and then we'll get there, okay? So now let's see. It's still animated, okay? So that's P1. We are walking through, we are starting from what? This part, okay? So the P1 is given, this part here. Plus pressure due to a mercury and then the distance or the depth or the height L3. This is it, okay? Gamma L, but the gamma here is what? Gamma mercury. Remember, we are going down, so positive. Then minus the pressure due to what? The air column, which is gamma air times what? L2. This is the height, right? So it's also moving up, negative. Now, remember here is also off. We are here now, so we come down. Remember when we move here, we're supposed to go down, come here, that, right? But we are not interested in this. And remember, if you move this way, it's the same value. So the value here is the same thing as the value here. So it doesn't matter as we move in the horizontal direction. We are only interested in the elevation, the height. So over here, we will go, and then we are here. We are left with this small part. So plus, we are coming down. This thing due to what? The oil column, the small part. So we have it here. Okay, that's the blue one. So that is what? L1 from here to here. And we don't have any column because from here we'll move down here and then we'll come. Then we are at the point there. So that is what we equate then to what? The pressure P2, which is what? The pressure of the air we are looking at. So once you get this done, you are done. So good. This is just a strong revision, right? All right. So, but the data given as follows. Let's see. We're given this information. P1 is open to atmosphere, so that will be 0. Mercury is that. Oil is that. L1 blah. We change everything to meters. P2 is what we don't know. So upon substitution, we have this. Now, remember they didn't give us that of air, right? But we're told to neglect changes in air. So we will just neglect that. So we take this air out, okay? Neglecting pressure changes in air. So this part already is 0. P1 is 0. This part is gone. Okay, I just rearranged this. I brought the P air or the P2 here. And then we had this. Okay, that's what is happening here. Okay. Mercury is there. L3 is that. Okay. All right. So with this, I can now simplify and thus obtain what? The P3 or the pressure of the air to be this value, 109.54 kilopascal. Please, the unit, I'm very serious about it, okay? Try to understand how to obtain those things. Yes, I know you have a lot of questions. If none, just relax. But if you do have any question, please write them down and ask me. Okay, use the timing in the video and get me the questions and I'll answer them for you, okay? Thank you very much. Let's hold on and then wait for the next option, okay? That's from 5 going. All right, sorry, from 6 going. Thank you very much. Enjoy your time. Bye-bye.